Hey guys, so this is going to be part 2 of our lecture series on chapter 5 section 1 on the antiderivative. So I just finished wrapping up editing. The first part should be uploaded to YouTube by this point, and the first thing I'd like to point out is, oh my god, do I really sound like that? Man, I'm sorry. Okay, with that aside, quick recap. Last section, or last part, what we did is we went through section 5.1 and we attacked the theory of anti-differentiation. Now, in this part, what we're going to do is more examples. This entire video is just going to be dedicated to doing examples of anti-differentiation. So, let's get started. All right. So, this is going to be the setup. On the left side, we've got our two main rules that we have right now. The power rule, which is this guy. And then we have the log rule, which is this guy. And the power rule states that the integral of x to the n dx is equal to x to the n plus 1 divided by n plus 1 plus c. Now, the second rule is our log rule. The integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. Now, we're going to take these rules along with the properties we went over in the last section and do some examples. Okay, so let's see what we got first. First up, we want to take the integral of x squared plus 4x cubed with respect to x. So let's do that. So we have the integral. Wow, that's really thick. Let's not use that one. Let's try this one. The integral of x squared plus 4x cubed dx. Well, now we're going to use that property where the integral of the sum is the sum of the integrals, and we get this is equal to the integral of x squared dx plus the integral of 4x cubed dx. All right, now we have broken this up into two singular integrals, the integral of x squared and the integral of 4x cubed. So both of these, it's some constant times x raised to some power. And what I'm going to go ahead and do is pull that constant 4 out in front, just like this. Remember, properties of the exponents allow me to do that. They behave nicely. I like doing things like this. I like to pull the constants out in front, call it a day. Now we want to use this guy. We want to use the power rule. And so this first integral, well, we have x squared. So in this case, n is equal to 2. So we're going to rewrite this as x to the 2 plus 1 over 2 plus 1. Now we need to add that integrating constant, or our houseboat, as we called it in the last video. But I don't want to use a bunch of c, so I'm just going to call this one c1. I'm just going to go ahead and call it c1. Plus 4 times, now we take the integral of x cubed. Well, to do that, we use the power rule over here again. And we accept this time our n is equal to 3. And we get x to the 3 plus 1 over 3 plus 1 plus our integrating constant, c2. Now do you see why I called it c1 and c2? Otherwise, we'd have two c's, which would imply that the constant is equal to the same thing. It's a big old mess. Going to avoid that, but it's calling one of them c1 and the other one c2. Now, let's combine some stuff. This is equal to x cubed over 3 plus c1 plus. Now, here we have 4 times something divided by 3 plus 1, or 4. That's going to cancel. And we're going to be left with x to the 4th plus 4c2. Now here's where things are going to be a little strange, because this is a constant, and this is a constant. Then we have a constant plus 4 times a constant. What's a constant plus a constant? It's another constant. So I don't really care what it is. I'm just going to call that C. I'm going to group C1 and 4C2 into one constant, and we're going to call it c. So we get x cubed over 3 plus x to the 4th plus c. This is our answer. This is the antiderivative to this guy. Quick way to tell, take the derivative of this and make sure you end up with this. So this is the process that we are going to go about in taking antiderivatives. All right? Everyone with me so far? Okay, I'm not entirely sure why I asked the question to my camera. I guess I'm used to lecturing in front of people. And since the only people in my room is the person sitting over there in the corner and then my dog, neither one of them is going to respond to me. So I'm going to keep asking questions nonetheless. All right, side tangent over. Now, that was the integral of this polynomial. Let's see another situation. What if we wanted to integrate 3 over x dx? Well, now it's probably safe to assume, given that we have something over x, that we're going to want to use this one. So let's take this. The integral of 3 over x dx. Well, once again, integral has the nice property of where we can pull constants out in front, so that's what we're going to do. So we get 3 times the integral of 1 over x dx. All right. Well, what is the integral of 1 over x dx? It is that. It comes from that log rule that we proved in the last video. So this is equal to 3 times the natural log of the absolute value of x plus c. So, a couple things to point out. When we're doing this log integral, don't forget these absolute value bars right here. We have to have the absolute value bars here. Otherwise, we break the natural log function. If you're not sure why, go back and watch the previous video in this rule. We talk about it a little more there. And then we have our houseboat here again. It's just some plus c, some constant we have to tack out in front. Quick way to check that this is in fact the antiderivative to this. It will evaluate the derivative of this and make sure you end up back here. All right. Seems straightforward enough. Notice kind of a trend we've been doing here. What we're doing is we're undoing the derivative. We're given a function and we're basically told to assume it is the derivative of another function. So what we do is we have to try and quote unquote guess what that original function was that we took the derivative of to end up with this guy. Now, this is an example of the log rule. Let's see another example. Here, we have the integral of 5 times the square root of x. Now, that one looks weird. We have the square root of x in there. We do not have a rule for the square root of x, do we? Well, to answer that question, the first thing we need to do is rewrite this. Whenever you're given a problem in a weird form, the first thing you should always do is try and rewrite it into something simpler. So, 5 times the square root of x dx, that is equal to 5 times the integral of x to the 1/2. Because the square root notation, that little radical right there, we can just rewrite it as a fractional exponent, which I realize looks like 2 over 2. So we're going to rewrite that as 1/2. So 5 times the integral of x to the 1/2 dx. Now we have a rule that can handle this. The power rule is just for some n where n is not equal to -1. Now take a quick second. Why can n not equal -1? Well, go back and look at the other video for a little more details on that. So 1/2 is a number. We can use the power rule. So let's do this. So this is equal to 5 times x to the 1/2 plus 1 over 1/2 plus 1 plus some constant c. Well, this is equal to 5 times x to the 3/2 divided by 3/2 plus c. Well, this is just equal to 10x to the 3/2 over 3 plus c. Now here, I kind of cheated. Technically, this is the same c as this one, but the reason I can still call it c, even though we multiplied it by this 5 right here, is because it's still some constant. You have a constant, you multiply it by 5, you still have a constant. We don't know what it is, so I don't need to change that. I'm just going to keep calling it c. All right? So this is how we want to integrate the square root of a function. Rewrite it in terms of an exponent, then do the power rule. It's exactly like how we would have taken the derivative, except we're going the other way. We're undoing the derivative power rule. That's what we are trying to do. All right. That's enough of that example. Let's see another one. Whew. Well, that just looks fun. All right. So we have the integral of x squared plus the 4th root of x plus 7 over x squared dx. So just like in every situation we've accomplished so far, the first thing we want to do is write it in a simpler form. Well, so we get the integral of x squared plus x to the 1/4, because that is a 4th root right there. So we need to rewrite x to the 1/4 plus 7 divided by x squared with respect to x. Okay. Well, what we're going to do is we're going to divide each term individually. So this is equal to the integral of x squared over x squared plus x to the 1/4 over x squared plus 7 over x squared dx. Let's put brackets around these guys. Well, that's just equal to the integral of 1 plus x to the negative 7/4 plus 7x to the negative 2 dx. So all I did here was I canceled terms. Here, I used properties of exponents to get x to the negative 7/4. And then here, I just rewrote 7 over x squared as 7x to the negative 2. So remember, negative exponent just means take the reciprocal. Now we can integrate each term individually. So this is equal to the integral of 1 dx plus the integral of x to the negative 7/4 dx plus the integral of 7x to the negative 2 dx. Now for each one of these, we're going to do the power rule respectively, because we might have some weird exponents, but we still have exponents that are not equal to -1. So we are just going to do the power rule 3 times. Well, the integral of 1 dx, well, what is the integral of 1? Remember what the integral is. It is finding the antiderivative. So we need to ask ourselves, the derivative of what is equal to 1? Take 3 seconds to think about that. The derivative of what is equal to 1? Well, that's just equal to x. Now, for each one of these, we're going to have some integrating constant. I'm just going to combine them all at the very end with one big plus c at the end. So don't even worry about that right now. That's equal to x plus, well, we get x to the negative 7/4 plus 1 over negative 7/4 plus 1 plus 7 times x to the negative 2 plus 1 over negative 2 plus 1 plus our integrating constant. Now this just becomes x minus 4 over 3x to the 3/4 minus 7 over x plus c. Now, what I want you to go through as an exercise to prove these two things are equal to each other. So simplify that, simplify that, simplify that, simplify that, and then show that from this gets you here. So that's an exercise for you to do on your own. Now, that's that example, and we ended up with this answer. What this is saying is this guy is the antiderivative to this. If you differentiate this and then you manipulate it algebraically, you will end up with that. Remember, that's always a good way to check your work. If you have a function you think is your antiderivative, take the derivative of it. Make sure you ended up where you started. Remember, the derivative and the antiderivative are related to each other. So we want to take the derivative, our antiderivative. If we end up where we started, voila, we have our answer. As long as you remember that little houseboat right there. All right, that's enough of that example. Let's look at another one. Evaluate the indefinite integral of the integral of cosine x dx. Now, we do not have a rule for that. We have a power rule and we have a log rule. We have nothing on trig functions. This is where our intuition on derivatives is going to come into play. The reason why I emphasize so much in chapter 3 that you had to have your derivative rules memorized. What the derivative of sine is, what's the derivative of cosine, things like that. And this is why. Now we have to go backwards. We were given a trig function. We could take the derivative of it and end up with another trig function. Now we have to go the other way. So to evaluate the integral of cosine of x dx, what we have to ask ourselves is this. The derivative of what is equal to cosine of x? So let's write that down. So the derivative of what is equal to cosine of x? So the derivative of what is equal to cosine? Well, if we remember our trig rules, the derivative of sine of x is in fact equal to cosine of x. Because when we take the derivative of sine, we get cosine. So if we're taking the integral of cosine, well, that's going to send us back this way. So what we can conclude is the integral of cosine of x dx is in fact sine of x plus c. Can't forget that houseboat. Can't forget that houseboat. So this is how we evaluate the integrals of trig functions. When we got something basic like cosine or sine or tangent, squared or something like that, when we know what the trig rules are, then it's just as simple as remembering the trig rules. That's why we got to have those rules memorized, guys, because now we're doing it backwards. All right. So we've concluded that the integral of cosine dx is equal to sine of x plus c. Don't believe me? Differentiate sine of x plus c and see if you get cosine of x. All right. That's enough of cosine. Let's go on to the next example. The integral of sine x dx. Since we do not have a rule over here yet, we do not have any kind of rules for this, we have to use our knowledge of the derivative again and ask ourselves, the derivative of what is equal to sine of x? Well, that last problem, we used that the derivative of sine of x is equal to cosine of x. So it makes sense that when we're integrating sine of x, we need to use cosine of x. But what is the derivative of cosine of x? That's just equal to negative sine of x. Now that's real close, but there's a slight problem in this and this. This negative right here. That's a problem. But what if we take this negative and we move it to the other side? Essentially multiply both sides of this by negative 1. So we can conclude that negative ddx, or another way to put it, the derivative with respect to x of negative cosine of x is just sine of x. So the derivative of negative cosine of x is equal to sine of x, which tells us that negative cosine x is the antiderivative of sine of x, which is exactly what this is asking us to find. So we conclude that the integral of sine of x dx is equal to negative cosine of x. Is that correct? No, it is not. We forgot our houseboat, that plus c. When we're dealing with an indefinite integral, we just got to get into the habit of tacking on that plus c at the end. We just got to get into that habit. Do not forget your houseboat. So the integral of sine of x dx is equal to negative cosine of x plus c. This is how we handle integrating trigonomic functions. We look at it and we have to think through our trig rules and try and work backwards to figure out what the antiderivative is using the derivative trig rules we already know. All right? Well, let's see another example of a trig function. We have the integral of secant t tangent t dt. Now notice, this is with respect to t. It's no longer with respect to x. Is this a problem? Is the fact that our variable is now t and it's not x, does that give us a problem? No, because these functions are in terms of t and we are integrating with respect to t. So all the variables line up with each other, so we are good to go. Now we have to ask ourselves this question. The derivative of what is equal to secant times tangent? Well, if you remember your derivative trig rules, hint, hint, you need to know those, we get that the integral of secant t tangent t dt is equal to secant of t plus houseboat. Don't believe me? Well, let's differentiate this. Let's see what happens. We'll take d dt, because our variable is t, of secant of t plus c. Well, that's just equal to the derivative with respect to t of secant. But what is the derivative secant? Secant tangent, which is exactly what we have right there. So this thing we claimed to be the antiderivative, we took the derivative of it, and we ended up back where we started. So we can conclude that our initial guess is correct. The integral of secant of t times tangent of t is equal to secant of t. It's a nice little trick to understand the relationship between derivatives and antiderivatives. So when you have a guess for what the antiderivative is, take the derivative of it. If you ended up back where you started, you're good to go. You have your answer. All right, that's enough with this one. And by the way, if you have any question about any of the slides that I have done so far, what I want you to do is write it down. Write down the slide number or take a picture of the slide, but any kind of information you can about what the slide is. Send me an email. Say, at this time in the video, I didn't understand what you meant. Can you explain this in more detail? You need to send me the slide or a time in the video where you have a question. Just send it to me with your question, and I'll write up a little more detailed answer for you, and we'll clear up any understanding you have. Since this is an online lecture and you cannot stop me in the middle of my lecture to ask any questions, this is what we're going to have to do. Just jot down where you have a question, what your question is, shoot me an email after you watch it, and then we'll get that all sorted out. All right. Well, that's enough of secant tangent. Let's look at another example, because once again, the trick to integration is practice. There is no secret magic 8-ball clicking moment. It's just practice. And eventually, it's just going to become second nature. You just do problem after problem after problem, and eventually, you'll be experts at this. Now, let's look at this new problem. The integral of dx over the square root of 1 minus x squared. Now, that just looks awful. We have a fraction, we have a square root, and inside the square root, we have another function. This is just a nightmare for us, okay? This is one of those situations when you look at a problem that's this gross, you need to take a second and relax. Stop and think. First thing I want to do is I want to rewrite this. And we get 1 over the square root of 1 minus x squared dx. The dx, this operator right here, I can multiply things by it. I can move it up. I can move this dx up in here. 1 times dx is just dx. That's no problem for us. So we have the integral of 1 over the square root of 1 minus x squared dx. Now we need to stop and ask ourselves this. The derivative of what is equal to 1 divided by the square root of 1 minus x squared? The derivative of what is equal to 1 over the square root of 1 minus x squared? That is what this problem is really asking. The derivative of what is equal to 1 over the square root of 1 minus x squared? Once again, this is why we got to know our trig rules. That That sheet I posted on Blackboard with all the derivative formulas has all of these formulas. But when we're integrating, we're just going the other way. So rather than taking the derivative of a function, we are asking ourselves, the derivative of what gets us here? So if you go back and look at that worksheet and you try and figure out where this is, you'll actually notice that the derivative of arc sine of x, or I guess another way to write that would be sine inverse of x, is equal to 1 over the square root of 1 minus x squared. Yeah, inverse trig shows up too, guys. It does. It doesn't go away. So from the properties of derivatives, we know that the derivative of inverse sine of x is equal to 1 over the square root of 1 minus x squared. So that means the integral of 1 over the square root of 1 minus x squared dx is equal to sine inverse of x plus our integrating constant c. So that is how we evaluate that derivative. Right now, the only tools we have in our belt are the power rule, the log rule, and the rules of derivatives that we already have. The list of those trig rules, the list of those exponential rules, all those rules that we've compiled in that list we have, those we got to know. Because a lot of integrals get a whole lot easier if you know those derivatives. Sorry, I just lost my train of thought. My dog just waved at me. How do I not pet him now? Okay, I'll pet him in a minute. All right, let's look at another example. So we have the integral of secant squared of x dx. So the exact same process we've been doing. When we want to integrate this trig function, we have to ask ourselves, the derivative of what gets us secant squared? Well, you look back at those rules. We get the integral of secant squared of x dx is equal to tangent of x plus our integrating constant c. How do I know that? Because the derivative of tangent x plus c is secant squared x. I cannot say this enough. We got to know the derivative of those trig functions. On your gateway exam, on your final exam, I promise you, the integrals of trig functions are going to make an appearance. They just are. So we got to have these rules memorized. There's no way around it. We just got to have these rules memorized. So the integral of secant squared of x dx is equal to tangent x plus c. And my heart just died a little bit because I was really worried I didn't click record, but it looks like I did. Okay. Whew. I need to calm down now. All right. Let's see one more example. The integral of e to the x dx. Now this is the most different example that we have seen today. We have seen the integrals of polynomials, and for integral of rational functions, integral of square root functions, and trig functions, and inverse trig functions, and now we have exponential functions. So this is a different situation, but our technique remains the same. The integral is just trying to find the antiderivative. So we have to ask ourselves, the derivative of what is equal e to the x? Now remember, e to the x is a famous function. It's a powerful function. We love this function. It has got some really nice properties. In particular, the derivative of the exponential function is itself. So what that means is the derivative with respect to x of e to the x is equal e to the x. That's why this property is so important. It makes integrating exponential functions so much nicer. So much nicer. Because when we have the integral of e to the x dx, well, that's just e to the x plus our integrating constant. So that's how we're going to integrate basic exponential functions. Now notice all the functions, excluding the polynomials, that we have tackled today have been relatively simple. They have been straight rules that we know. We know these rules. We have them by heart. We have our list. We know these rules. But none of them are too terribly complicated functions. It's not like sine of 2x plus 7 where we have to use the chain rule. Notice none of the things we did involve the chain rule. That's because when you integrate something where a chain rule was involved, we have to use a lot more machinery to get that job done. The problem gets a lot more complicated when we have to deal with the chain rule. So right now, we are just focused on the examples where we do not have to do that. We're going to hit the kinds of problems that require some kind of chain rule technique in section 5.5 called use substitution. But I believe that is next week's problem. This week, we're just focused on basic examples, basic properties, and hammering home the fundamentals of what anti-differentiation or what indefinite integration is before we go on to the more complicated stuff. The reason I'm going on this little tangent is because I need you guys to understand the importance of having the basics down. Do not blow this off until the last second. Because if you wait until section 5.5 to try and learn this stuff, you're going to have a really big problem. So take this week, watch these lectures a bunch of times, and hammer home the fundamentals of integration before we move on to section 5.5. Well, that wraps up section 5.1. Now the next video or two that we're going to do is going to be on sections 5.2 and 5.3. Now 5.2 and 5.3 are directly related to each other, so I'm going to combine them into one lecture. And that lecture is on what we call area under the curve. So we're taking a little break from this indefinite integration, this anti-differentiation stuff, and we're going to go talk about some geometry, some measurements, how to measure the area under a curve. All right, guys, I will see you next time.